Welcome everybody. Okay, so what we're going to talk about today is how to tell where time goes in your program, and that's the key step in making your program faster. So important for milestone 2 to try to make things fast, and also important in milestone 3 and 4. So all of them performance is rewarded. Okay, so what do you know how to do in terms of figuring out where time goes? So you know big O analysis, and it's a powerful tool. So you know that an order n squared function, for example, will eventually take longer than order n log n, for sufficiently large n. So if n is small, you don't really know which one's faster, but if n's big, n squared is eventually going to be slower. And the standard template library that you're using tells you the complexity of most functions. So if you're using a standard template library and writing loops, you can figure out what the big O of your functions are and see, does this seem reasonable or not? Think about how to make it better. And that's where you actually want to start. Try to get a good big O solution. That's your biggest hammer. You can also, so that's the biggest impact. I showed early on in one of these tutorials the difference between an order n algorithm, or actually an order n squared algorithm versus an order n log n, and it's enormous. So that's where you want to start. Once you think you've got the big O of your key functions down to as small as you can get, you can still optimize some more. So in EC244, you spent a lot of time thinking about when is a copy constructor called, etc. So that's another place where sometimes a program can get slowed down significantly if you're making copies of big data structures. So copies of little things like floats, integers, doubles, pointers they don't really amount to very much. But if you do a deep copy of some big data structure, like an entire map or an entire unordered map or entire vector, okay, that can actually start to hurt. The challenge here is you still tend to be guessing. You're looking at your code saying, is that a copy constructor? Is that not? What you were taught in 244 is a bit simplified as well. The C++ standard has gotten more and more advanced in terms of the optimizations it allows. So it tries to get rid of a lot of copies. So what might look like a copy may in fact kind of be optimized away by the compiler. But it can't always be optimized away. So it is better to pass big things by reference and try to avoid copies of big things. But it can still be hard to guess, is this actually slow or not? And then you can start going, okay, well, I don't know, I've got this loop and I've got like 3 variables assigned. Maybe I can rewrite it to have 2 variables assigned in a different way. Maybe that'll be faster. That tends to not be very good, okay? Because now you're just guessing. And it's actually hard to predict, unless you have a lot of experience, what's faster in a program when you get to that low level of detail. Because there's all this optimization going on and you've got this very complicated processor chewing through it. So it tends to be not very accurate when programmers just start guessing what's fast and what's slow. You can also time, if your program takes long enough, you can actually just take your stopwatch and time it and do tests. But you can only do that if operations take a long time. So we'd like to get some more tools in the toolbox. And Lord Kelvin, everybody probably knows something Lord Kelvin did. Any idea what Kelvin is responsible for? Kelvin temperature scale, right? Okay, so Lord Kelvin said, if you cannot measure it, you cannot improve it. Maybe why he was focused on measuring temperature. So this is an engineering truism. You can't really optimize things if you can't measure them. So this tutorial is all about measuring. It's not really going to tell you that much about how you speed things up. It's about how do you figure out where they're slow. Okay, so how do we measure them? So we can do manual measurements. And a crude manual measurement would be the stopwatch on your phone. But again, that's only going to work for pretty long times. And it's going to have a pretty large error bar. So we can do manual measurements. And I already talked about this in lecture, but I'll show you a few more techniques on this. So you write code to measure time. The advantage of this is it has the lowest overhead. Like what I mean by overhead is it doesn't impact your program very much. The code that you write to say how much time has this taken, it doesn't take very much time, which means it's not very disruptive. Gives you a very accurate answer. Probably it's the most accurate answer of any technique we're going to use. And you can measure not just how long it takes for a function, but even like pieces of a function. If you want to know how long does this loop within a function take, you could check that. Disadvantage of manual measurements is this. We have to write code for each one of them. So it takes us some time and some effort to write that. Another technique that can be useful, it's easy, it's fast, it can give you insight into where you're spending your time, but it's not going to give you really detailed measurements, is use the debugger. So in the debugger, there's a pause button. And after you hit the pause button, you can do anything you want. You can go, so usually you've been probably using breakpoints to stop your program. But you can actually stop your program anytime you want by just hitting a pause button. And then you can go look at where am I? What function am I in? What are the variables? What am I doing? And if you do this 5, 10 times and you find you're always in the same spot, it's a good sign that's where you're spending most of your time. That's where you should start optimizing. So its disadvantage is it's coarse. You can only hit pause, not very fast, right? You might be able to hit it once a second, once every 2 seconds. So you can't use this to time really small things. Advantage is you actually, when you pause it, you're inside the debugger. You can look at everything, not just which function you're in, but all the variables and so on. And then the last technique is called using a profiler. Who's heard of a profiler? Have you ever heard of these terms before? Okay, so a profiler is a standard technique. Pretty much every programming language has them. So we're going to talk about doing it in C++, but the techniques are similar in other languages. So a profiler is essentially an automated way to do this, right? You're hitting pause and you're looking at where am I. A profiler does that for you, and it does it about 1,000 times a second. So in 243, have you learned about interrupts yet? Okay, so a profiler uses interrupts. It interrupts your program, and it checks where am I? What function am I in? It records that, and then it says continue. And then it does that about 1,000 times a second while your program is running, and it's recording where was the program every time I stopped it. It records a little more information, like how did I get there? I'm in this function, and I got to this function I'm in function A, and I got to this function because function B called it. So it records all that, and when your program ends, it writes that out to disk, and you can use tools to visualize it. Look at where did I spend my time? So it's like a really fast version of this sample using the debugger. You're never going to click 1,000 times a second, and you're never going to write that much data down. So advantage of that is, you get more detailed reports than you'd ever get by doing this, just pause and continue yourself and writing numbers down. Disadvantage is that there is some overhead, okay? The program is being interrupted like 1,000 times a second. That does impact its runtime some. So the more accurate, the more detailed the information you're getting from the program is, the more you're kind of disrupting it. So there's a little bit of Heisenberg uncertainty principle here. But this profiling also works well. And it works well for identifying bottlenecks. You've got a program that's, you're just really not quite sure where the time is going. Maybe it's spread across 5 or 6 routines. Profiling can give you very detailed information to say, okay, if you're going to spend your time optimizing, here's an ordered list of where to start optimizing. Start with the things that have a lot of time. Okay, so we're going to go through each of those things, just kind of demonstrate how they work. So measuring performance manually is basically get the time before some region of interest. Okay, whoops. And why did it do that? Oh, I see, okay. Sorry, I don't remember my own slides. So get timestamp before the region of interest, get the timestamp after the region of interest. So maybe it's an entire function, maybe it's a loop nest. Subtract before from after, and then output. Okay, so that's how you get the time. So that's what's the time now, what's the time when I'm done, subtract them. Okay, so let's take our act on button press function that we wrote last class. This isn't actually a good one to, you probably don't care that much about this one because it's probably fast enough. People can only click a button at a certain rate. But if you found that your button click responses were really slow, you could say, okay, let's put a timer in there to just see what's going on. So this is the code that we wrote. Where should we put the get time? If I want to know the whole runtime of this function. So where should I try to get the initial time? What do you think? Right, so I should get it right here, right at the start. Okay, and that's what I've done here, okay? So there are a few different functions you can use to time things. The chrono library is pretty powerful, so that's what we're using. Part of the C++ standard library. Syntax is a bit baroque, so just the slides are posted. You can go grab these lines from it. So this just says in the standard library, So standard namespace. There's actually a sub namespace. So I put chrono functions in another namespace inside that one. So in standard chrono, there's a function, there's a class called high resolution clock, and I want to call this method now. And I can actually call that method without an object because it's what's called a static method. So you call that and you get the time. And it returns this chrono object. I don't care what that object is. I'll just say auto. So there's some object, get it. Okay, I do my work. And now I have to get the timestamp after the region of interest. That code is going to look identical. Okay, I'm just going to ask for the time again. Okay, I'm just stored in a different variable. So I'll store it in this variable end. Okay, but it's the same call. Calculate the time difference. Okay, so I subtract them, and those objects have overloaded the subtraction operator, so it works. They're objects. They're not. They actually have all sorts of data in them. So I actually am going to do this thing. Okay, so it's called a duration cast. So it's provided by standard chrono, provides this function duration cast, and I'm basically saying turn this into seconds and store that in something called delta time, and then print it out. So now I print out, I'm in act on button press. That's the name of this function. So I decide I'll print that out, and I print out the time. Okay. So you can stick that all over your code. And now you've got timers, and they'll be helpful to you. Okay, so that's useful. I might decide I want to have this timing code in my program all the time. And in that case, it might get kind of visually distracting to be printing it to the screen all the time. So instead of printing it to the screen all the time, I'm now going to print it to a file. Okay? So here's the way I'm doing that. I'm going to open a file. Here I'm opening it. It's a global variable, and I'm opening it just in a constructor, which means it gets opened when my program starts. Global variables are constructed and initialized before your main function starts. So at the very start of my program, this basically says output file stream. So it's an output file that I can write to just like cout, behaves like a stream. I gave the object a name, profile CSV file. CSV because I'm going to use comma separated values. So value, then a comma. That makes it easy to read it into spreadsheet tools. And I have the name of the file here. So I'm going to call it actonbuttonpress.csv. Okay, so logical places for me to open this file would be maybe in load map or maybe at the start of the very start of the program. I've decided to do it at the very start of the program. Okay. And then I've written this little function called profile CSV. And basically, it takes a start time and it takes a string, which is the name of the function that I'm profiling. And this is a little helper function. I'm basically making my code as short as possible by taking the repeated lines that I'm going to use to profile code and putting them in a little helper function. So it takes a starting time and it takes a name of a function. And basically, I get the time right now, and I call that end time. I do what I just did. I subtract the end time from the start time from the end time to get how much time has passed. And I print out, using the same code I had before, the time in seconds. And so I can tell what the heck that time's for. I print out this func name, this string that was passed in. So, I mean, it might not be a function name, but I'm calling it func name to say that's probably what you want to pass in. It's the name of a function and a start time. And I'll tell you how much time has passed since that start time, and I'll write it to a file. So it writes it out to a file, and it puts commas in between the name of the function and the time that has passed. I've put if-defs around this. Does anybody know what these if-defs do? You've seen these before? So I see somebody nodding. Okay, what is that if-def for? Like, what does it do? Why would I have this? Any idea? Yeah. Yeah, so this is, well, so basically, no, this isn't an if-def once. This is like, if-def is a general thing saying, if this variable, I can define it with somewhere in my program, in some header file, which I haven't shown here, or in my make file, I can basically define this. So I can define profiling. So if I do that, okay, profiling is defined and this code will be compiled. Okay, if I comment this line out, then these lines will not be compiled. They will not exist in my program. So this is a convenient way to put essentially extra debugging or monitoring code in your program that you can turn off really easily. So if I decide I don't want to print this file, because maybe I submit and I'm worried about generating lots of output, because maybe that'll slow me down a little bit, or I'm just worried about it, I can turn it off really easily with just one if def. Does that make sense? So if I do not have this defined profiling somewhere before this, usually I'd put it in the header file, the control that everybody includes. So maybe m1 internal.h or something. Then this will get turned off. Okay. As long as I define profiling, it'll be compiled. If this totally confuses you, you can go, well, if you always wanted this code to be active, you didn't ever want to turn it off, you could just do this, right? You could say, get rid of that if def, okay? So it's just a way to like take code in and out of your program under your control. Okay, so that's my helper function, because basically I'm going to put these profiling calls in multiple places in my program, so I want to make them as easy to use as possible. So in my act on button press, the routine I'm actually trying to time, all I have to do now is at the start of the routine, I get a start time. So I call chrono to get that. And then I call this little helper function, profile CSV. I pass in the starting time, and I pass in the string I want it to print out. So it's going to say how much time has passed since that starting time, and it's going to print whatever string I passed in, and then the time that's passed. And I'm passing in the name of the function, because that's kind of a reasonable way to do this. And I'm not printing it to the screen, okay? I'm printing it to a file, and I'm printing it in comma-separated value format so that I can bring it into a spreadsheet tool. You guys with me? So this is a reasonable way to add kind of manual profiling information into your program. I also basically, at the end of every line, I say new line with this standard end line, because I want these to be one line per piece of profiling information. And this also makes sure that the output comes out right away. So cout files and your cout, your standard output, are allowed to be buffered, meaning they don't actually have to send anything out until the program ends, or you send endl, okay? Endl says actually write it out. So in case I'm sitting there watching this as the program's running, I'd like it to actually write it to the file now, not later. So I say at the end of every line, I'm putting in the end line, or endl. You've probably usually seen this as endl. Okay, so what is this going to look like? It's going to make me a little spreadsheet. And I just did this for act on button press. But if I go and put this in a bunch of different functions, I'm going to see, I can get a little spreadsheet that shows me how long every one of those functions took every time it was called. Okay? So let me go and demo that. Okay, let me make this a little bigger. Okay, is that big enough to see, or should I make it bigger still? Do people see that text, or should I go one size bigger? No, can't see it? Okay, I'm going to go one bigger. So let's see. Okay, let's go to, all right, let's try 20-point font. Okay, how's that? Is that visible? Okay. Oops. Okay. Okay, so inside this program, I've already basically gone in. I've used that little helper function called profile CSV that I just showed you. And basically in a bunch of my redraw functions, I put in code that says, at the start of the function, get the time. And at the end of the function, call this profile CSV and pass in the starting time. Profile CSV grabs what is the time right now, figures out the difference, and it's going to print to a file, the name of the function. So that's what I'm passing in here, and then elapsed time. And if I go look at what does this look like, here's my, let's go to the definition. Okay. Let's see. Where is profile CSV? Okay, interesting. It's not going to my profile, to my definition for me, but let's go look here. Okay, so this is basically the function I just showed you, right? This is the exact code that was written up there. Okay, so I'm going to time this. What build should I use when I'm going to do timing measurements? What do you think? Okay, here are my options. Here's my menu. Which of these builds do you think I should do? Yeah, so I'm going to do release. I could time the unit tests. I've decided I want to just time my actual mapper, so I'm going to use release. I want to use release because it's optimized, and I want the most accurate answers. So I'm going to make sure this is built. Okay, it is. I'm going to run it. Okay. So it's going through load map. So load map takes a few seconds. Okay, and it brought up Toronto. So now I'm going to just move this over here. Okay, so I'm actually trying to measure the time of my redraw functions. So I need to make some redraws. So I'm going to basically turn on display of subways. So my solution can show subways. I'm going to turn on display of like some street names when it seems appropriate and so on. And I'm going to start zooming in. Okay, so zoom in more. Okay, I've now got some text drawing, and I'll move over a little, and then I'll zoom out all the way, and I'll end. Okay, so now I'm going to go to applications, and there's a spreadsheet tool on here called Libreoffice Calc. Let's see, let's discard that. So this is basic spreadsheet tool. Okay, so the file that my profiling subroutine was creating was called funcperf.csv, CSV for comma separated values. So I'm just going to open that up. And it comes into my spreadsheet tool in nice columns and so on. I could actually do some math on this if I wanted to. So I could make several versions of this and do like, am I getting faster or slower easily? And I put basically these manual measurements, these profiling calls inside a bunch of key functions. So my load map took 9 seconds. And then let me show you my draw map function. Okay, so let me go back to M2. Okay, let's see. So find my draw functions. Maybe it's called draw with a bracket. Okay. All right. So my top level redrawing function is called draw. Okay, so it draws everything. And you can see it's doing the same thing of it's getting the start time. It actually calls a whole bunch of helper functions. Okay, so it calls a whole bunch of helper functions to figure out what's my zoom level, draw all the features, so the parks and everything. This is some additional code that, again, if I do that define trick, so if I define debug draw intersections, it'll draw this, but right now it's not defined, so that won't get called. It draws all the segments. That's actually the road segments, so street segments that put some text on the points of interest, put some text like labels on the roads. And later on, we've got traveling salesman algorithm, but we're not using that yet. And if I've turned on the subways button, it draws the subways and so on. And at the very end of this routine, I basically call my profiling routine and say, okay, how long did the whole draw routine take? Okay, and if I go into various routines on here, so let's say draw all segment or draw features, let's do that. Draw all features. Okay, so inside, one of the functions this was calling was draw all features, and it's also timed. So it's basically saying get the start time. It basically says if I'm supposed to draw features, then go through, do some checks about how zoomed in or out I am, and draw every feature. And at the end, record how long this whole thing took. Okay, so that's what the code looks like. If I go look at the spreadsheet that I've created, okay, load map took 9 seconds. And then this whole draw function took 0.29 seconds. And it was mostly in draw features. Okay, so I basically am timing the overall routine, and I'm also timing each component, like the helper functions. So drawing the roads didn't take very long, 0.01 seconds. And I didn't take any real time to draw anything else. All the other stuff was really fast. Notice that after the first draw, it gets faster. Okay, so the first redraw can be slower because the graphics library can actually be loading in things like fonts and so on the very first time, but it caches those. So I'm not too worried about the first redraw. I'm more interested in the second one. Second redraw, the features took about 0.03 seconds. Drawing the roads took about 0.01. Labeling things, I'm not really labeling yet, so it didn't really take any time. And the whole redraw was pretty fast, 0.04 seconds. Okay, I turned on subway stations. Subway stations were pretty fast, all right, less than 0.01 seconds. Okay, so what this is showing me so far is out here, for the first few redraws, it's pretty fast, 0.04 seconds for the whole thing. And most of the time is actually drawing features. And as I zoom in, let's see what happens. As I zoom in, the draw is actually getting a little faster. So it went from 0.04 to 0.035 to 0.03. So it's a little faster as I zoom in. Now I'm down to 0.03, staying there basically. Okay, so why is it getting a little faster as I zoom in? So I've already talked about this, but basically EasyGL pre-clips. So I'm drawing a whole bunch of streets and features, and as more of them are off screen, things are actually speeding up because it's faster to draw things that are just easily determined to be off screen. So, and my redraws are pretty fast. At a certain point, okay, so here, let me highlight this. Okay, so this redraw took 0.03 seconds. The next redraw took way longer. Okay, the next redraw took 0.33. Okay, so the difference between those two is that's the point. Now I'd have to be kind of careful. Maybe I'd even have to watch the CSV as it was being written. But that is the point where my level of detail modeling changed. As I zoomed in enough, if you are watching carefully, you see that at a certain point, we started drawing all the streets and more stuff. Where zoomed out, we kind of drew less stuff. And as I zoomed in, I eventually decided I'm zoomed in enough, I'm going to draw more. And it actually hurt my redraw speed a lot. So I went from 0.03, which is pretty good, to 0.33, which is not so great. So tells me maybe I should play with my level of detail modeling because there's a big change in redraw speed right there. If I look at the components, it's again features. So features took 0.28 seconds, the streets took 0.05. So streets aren't negligible, but they're not the main thing. Drawing the labels is not taking that long, right? So that I'm not being limited by text. Okay, I zoomed in a bit more, and let's just go check as I kept zooming in. As I kept zooming in, eventually you saw that like some text appeared. So now I'm starting to see some noticeable amount of time is being spent drawing text, but it's still 0.03 seconds for labeling streets, labeling points of interest, which is a lot less than drawing features. So drawing features is my number one thing. Drawing streets is number two. Labeling things matters only when I'm really zoomed in. It still isn't as big a deal. And the subway stations are super fast, so I should not touch those at all. Okay, and I can keep looking through this and see the same basic trends. At the very end, I hit zoom fit, so I zoomed out again and my redraws got faster again because the level of detail modeling said skip drawing most little things. So I'm pretty good when my level of detail modeling is kind of skipping the little stuff. Not fantastic when I'm zoomed in. And the main thing that's slowing me down is drawing features. So if I want to optimize something, that's what I should optimize. And mostly I'm wasting my time on other stuff. It's by far less important. Okay, so does that make sense? So I actually learned a lot by putting this in. And if I write it in my code and just leave it there, as we do optimization or try things, I can just get data very easily. And I can actually put this data in things like my oral presentation 1. Instead of saying, I think my graphics are pretty fast, I could actually put a little table in, and that looks a lot better. You could even show improvements as I did things. Okay, any questions on that? Or it's all pretty clear? And take that as clarity. Okay, let me look at the next thing. So that was technique 1 that I just told you. Let me get rid of this file. Okay, so the second thing I said we could do is let's build this again. We can just run the program and we can hit pause and see where we are. So let's do that. And I can do that in release build, or I can do it in any other build I want. I'm going to choose to do it. I could do it in release build. Just to show you a different build that's useful for this, I'm going to use the profile build. Okay, the profile build is almost the same as release build. It has optimization on, but it turns off one optimization. The optimization it turns off is called function inlining. Does anybody know what function inlining does? Okay, so there's an overhead to function calls. In 243, you've learned, I believe, the branch to subroutine instruction. Okay, so that takes some time. And before you call the function, you have to push some arguments on the stack and so on. So there's some setup, there's calling the function, and then to return data to you, it puts stuff on the stack and you go grab it. So there's some overhead to calling a function. If the function does a lot of work, that overhead does not matter, okay? If that function does a very small amount of work and you call it millions of times, then it can matter. So things like pushback. Pushback tends to get inlined because you tend to call pushback millions of times. Okay, that's a good thing. It means that it speeds up your little functions. But when I'm actually about to do, I'm going to hit pause and see where am I? What function am I in? Inlining makes it harder for me to figure out what's going on. Because instead of seeing I'm in a little function, I might just see I'm in the bigger function that calls it because the code for that little function has been pasted into the big function. The little function just doesn't exist anymore. Does that make sense? It exists in your code, but the compiler just kind of removed it. It pasted it in. It's as if you had written the code in line. It only does that for small functions where it thinks it's a benefit, and it is a good idea. But I can slow my program down some by running this profile build, and I will get more information about what function I'm in. So it is a trade-off. You could do this with release, and your answers are essentially more accurate. It's the real program, the fully optimized one. But you can't see as many little functions because some of them are just gone. So you don't get as much information. So I've chosen to do the profile build. Okay, and I'm going to run I'm not going to hit run, I'm going to hit debug. Okay, so it's now going to run it through the debugger. I haven't set any breakpoints. I'm just running the program. Okay, so it's starting to run. It's going to be a little slower than release build. And the little functions are going to be what's taking the extra time. So I have disrupted the program a bit. Okay, so my load map just worked, just came up. Oh, actually, I've got to do one more thing. Okay, so I'm going to be hitting this pause button to see where I am. And my redraw function is too fast. You know, it varies between about 0.03 and 0.3 seconds. I can't possibly click pause fast enough. So I'm actually going to go intentionally slow it down. So I'm going to slow it down in a way where the measurements are still useful. Okay, so let me go find my draw function. Okay, so what I've done here is I've actually wrapped a loop around the whole thing. Okay, so my redraw function normally goes through and does each of these helper functions. I've actually got a loop around it, and I'm going to say do 30 redraws. Okay, it's not a useful thing to do. I wouldn't want to leave this turned on in my final submission. But I'm going to stop debugging. I'm going to rebuild because I want that to go into my code. And then I'm going to fire the debugger up. And I've slowed my redraws down by a factor of 30, but in a way where they still spend their time in the same relative way. They just do everything 30 times. Okay, so I fire up the debugger. Okay, so it's going to go through load map. Okay, so now I'm going to basically I'm going to zoom in a bit because I know that where I hit my slowdown is when the detail kind of came on. I'm going to turn on subways. I'm going to turn on names. So my program doesn't show names when I'm zoomed out, but I also have a toggle that will never show names if that's off. So I just clicked on it so that it'll now show names and it'll show the subways. And I'm going to start zooming in. And this is going to take a minute because I've actually slowed my redraws down. So they're artificially slow. But I don't actually want to look at them yet. I want to get into where that higher level of detail was. Okay, we'll see how slow these are. Let's do another redraw, see if this is, okay, so it's not too slow yet. Redrawing again, okay. And pretty soon I'm going to show more level of detail, and that's going to be a lot slower. Because my redraws were about 0.3 seconds. I multiply it by 30, it's going to be around, 10 seconds. So it's going to be a little painful to watch. Okay, with any luck, this is going to finish drawing shortly. There we go. Okay, so now I'm into you saw it was a lot slower, okay? And it's because I'm drawing all these buildings and all these little roads. I'm going to hit zoom in. And now while it's doing the redraw, I hit pause. Okay, so I hit pause, and the program is basically stopped. And I didn't set a breakpoint. It's just stopping right where it was when I hit pause. I look at the call stack. So I click on call stack down here. And the lowest level stuff, I'm down in some library. I don't know what the heck this is doing. I don't care. Let me make this a little bigger. I basically just look at it until I get back to something I recognize. So I'm in draw all segments. So that's my helper function that draws the roads. Okay, so I'm drawing the roads, and it was doing this pushback in draw segment. So, okay, so drawing the segments was an issue. I'm going to start again, pause again. Okay, so I pause again. I go look at where am I. Okay, and I am again in draw all segments. Okay, so I'm drawing the streets again. I'm going to hit run again, hit pause again. Okay, I'm in draw all segments. This is telling me that I'm spending a reasonable amount of time drawing the roads right now. Okay, here I'm in draw features. Okay, so I'm in draw all features. I can go see which feature I'm drawing. And I'm in draw line. Okay, so this tells me I'm in draw feature, and I'm drawing it with lines. So I can go back even and look at why am I drawing this with lines, and can even examine some variables. Whoops, let me go back here. So I'm drawing this feature, and this particular feature is, whoops, says optimized out. So that's one of the things about not using a debug build. This variable is gone. I can't look at it. It's been optimized away. But I can tell this is not a closed feature because I'm drawing it with lines. Okay, so I can keep doing this pause and continue. So I hit pause again. I'm again in draw all features. And let's let it run for a little while. Okay, and I'm again in draw feature. Okay, and I was in this helper function that checks if it's a closed feature or not. So this is telling me, this is again in draw feature. So this is telling me something similar to what I found when I put timers in. Okay, the only two places I've ever been when I hit this pause and continue are draw feature, and that was my #1 place I was. And the #2 place I was draw all segments, which is drawing my roads. So I should work on features first and roads second. It's also interesting that when I looked at these features, most of them were actually drawing lines. So I might think that it's the closed features, the polygons, but it looks like I'm actually spending a lot of time drawing the line features. So if I don't think those are visually that important, maybe I should not draw them so much because they're taking a long time. So does it make sense? So by doing this pause and continue, I've been able to kind of figure out a reasonable amount about where am I spending my time. And the more I do it, the more confidence I'll have. Okay, so let me shrink this down. Go back here. Okay, so I kind of did two demos there. Basically, first we did timers, and we put them into a spreadsheet. But the limitation is we have to actually write that code to do the timing. We need to know what to measure. So then I showed you how to do this essentially manual profiling, randomly sampling where's the program by hitting this pause button. Okay? And you do that over and over again. You kind of see where am I. In milestone 4 or milestone 2, sorry, you're timing your redraw function, which can be too fast for you to hit that pause button very well. So I basically slowed it down. So I slowed it down by just executing it 30 times. So now I can hit pause and look at it. And I already mentioned this too. So we can use any build we want with this technique. Profile build is probably the best trade-off of it's pretty optimized. So it's pretty close to the real behavior of the program, but you see the little functions. You could also do release. Release, you'll get more coarse data, but it's even more the real program. So those are the two reasonable things to do. Okay, it's already demonstrated that. Okay, so the last thing I want to show you is measuring performance with a profiler. So profiler, as I said, is basically doing what I just did by hand, but like 1,000 times a second and then summarizing the results for me. So you usually do this with the profile configuration for the reasons I just talked about. You want to see more data. And then you can, the easiest way to do this is then run the exerciser with this profile option. So the exerciser will run a bunch of maps for milestone 2. We have a whole bunch of cities that you can run through the exerciser. So I'm just going to run it on Toronto. I just want to run one exerciser, one city, do a bunch of redraws like I just did, get the data. The data is a bunch of raw data that you can't really interpret easily. We have a profile visualization tool, EC297 profile visualize, and the data from the profiler goes into this file, perf.data. So I'm going to visualize what this data looks like. And I'm going to leave my loop that slowed my redraw function down by 30x in. The reason is I don't want to spend forever clicking around in my GUI, and I want the profiler to see most of the time in my redraw. I don't want to be seeing like all the top functions are in load map, which unless I do a lot of redraws, that's what I'm going to see. Load map's going to be the #1 CPU time thing for a while. Now, if I click on things enough, eventually the redraws would become the main CPU time, but to get that faster, I'm going to leave my 30x loop in there. Okay, so let me show you what that looks like. All right, so I've got profile selected, right? I could do release, it's also reasonable, but I'm going to do profile. I'm going to stop the debugger and make sure that it's built. Okay, and it is. I'm going to bring up a terminal. Okay, so I'm just going to put NetBeans in the background. So I can do that by hitting Control Z and then saying BG. So now NetBeans is running, but my terminal I can use again. The command was EC297 exercise, milestone 2. I just want to run one of the tests, which was draw Toronto. And I give it this extra argument profile, telling it I want to do profiling. Okay, so it's going to start up my program. So it's going through load map. Now the graphics are going to come up. So it just basically runs like normal. Okay, I'm going to move this over here. Okay, my redraws are going to be kind of slow again. So let me zoom in a few times. Let me turn on subways. Let me turn on all the names. And basically, as I'm doing this, it's gathering data on where do I spend my time. Okay, so I just want to zoom in a bunch of times, give it enough information, enough redraws that I can get kind of accurate data that I can summarize. Okay, and my zoom level, I think, is just switched. So this one's quite slow because it's drawing all that little detail. All right, so it did the slow redraw. I'm going to do one more slow redraw, and then I'm going to just hit proceed to end the program. Okay, that was my last redraw. Let's hit proceed. And there, the program ended. Okay, so if I look in here, I'm going to see there's a file called perf.data. Let's see, it's right there. Okay, and it's pretty big. What is that? That's 79 megabytes. Okay, so I don't want to look at that by hand. So instead, what I want to do is use the EC297 profile visualize, and you tell it the name of the data file. So it's perf.data. Okay, and it's going to chew through that data, and it's going to let me visualize it. Okay, and it's going to take it a few seconds to go through that because it is a pretty big file. Okay, so now it's brought it up. Okay, so let's see. Let me just show you what this looks like. So this is basically a graph of your program. Every box is a function, and in the function are two numbers. See, can you see this? Let me zoom in one more time. Okay, so in every box are two numbers. The first number, 11.4%, for example, for this function, is how much time was spent in that function and every function it called. Okay, so, and then the other number is how much time was actually spent inside this function, not the things it called, but the actual code in that function. So this draw Toronto start is like the start of my program. And it's basically, you can see there's a bunch of stuff here. There's like unit tests. You don't know what any of that is. It also doesn't amount to much time because this start of my program, this function was 11% of my total time. And it's all in the things it called, none in it. If I go through and look at, well, what did it call? It called a bunch of unit test stuff. I don't care about that. And then it eventually calls load map. I recognize that. And that's 9% of my runtime. And close map, that's 2%. So, okay, this is my setup code. I'm actually not trying to optimize. I don't care. So I'm not going to look any deeper. Right? If I wanted to speed up my load map, I could look down here, see what is load map doing. These arrows show, this basically says load map took 9% of the time, but it's all in the functions it calls. 1.47% of it, that's the label on this edge, is in something called hash things that this function called. Whoops. And 3.7% is in a function it called investigate OSM, and 4% is in load streets database bid. So I can see that on these annotated arrows. Okay, but I don't want to look at this anymore because that is the wrong thing. That's load map, and I'm not trying to optimize it. The functions that took, these are also color coded. So the functions that took more time are brighter. So draw Toronto took about 69% of my time. All right. And that's draw map. There's a bunch of like library functions. I don't care about any of those. I don't recognize them. I'm going to skip over them. But they also take almost no time. Like you can see in the brackets, every one of these is like basically nothing. They just call something else. This is all basically kind of setup code. Don't worry about it. Now we get into our code that we recognize again. So there's basically this redraw function in EasyGL, which is calling draw. Okay, this is my actual redraw function. And it says my redraw function took 87% of the time. Okay, so basically load map and close map took a little bit. I already looked at that. The rest is in my redraw function. There's 0% inside the function, 87% in the things it called. 70% of the runtime is in by drawing of features, 15% is in drawing of the segments, which for us is the roads. Okay, so this is showing the same thing that I've been seeing a few times now. Most of my time is in the features, and then the next thing is in the drawing the roads. I go look in the features, it basically says I spend a little bit of time trying to figure out the order to draw them in, but most of my time is actually in this draw feature function, which I call over and over again. I spend 15% of my time rendering polygons, 7% figuring out what kind of feature it is, and 35% or 34% drawing lines. Okay, and I can go deeper. Okay, so what is this telling me? Features is my big problem if I want to make this faster. Streets are next. In features, I'm actually spending more time drawing the lines, the open features, than I am drawing polygons. So this gives me hints of what should I go work on. And then I could run I could time again, I could run profiling again to see if it's better. And I should do that. It's actually really hard sometimes to know, are you making things better or worse? So you want to measure a lot. All right, does this make sense to everybody? So it's a pretty powerful tool. Because I turned off inlining, I get more function calls shown here, but my CPU time measurements are a bit disrupted. So I could also do this with the release build if I wanted and get a slightly different report. Okay, so let me exit that. One last thing I can show you is EC29. I can basically generate a different view of this data. Let me see if I remember the, I think this will tell me what the options are if I, okay, there we go. So I can go, I can have it, this EC297 profile visualize tool can also show me the data in a different way. So that's what's called a call graph, the usual way you look at profiling data. There's another way you can look at it called a flame graph, and that's what I'm generating right now. Okay, so the flame graph does not show me who called what. It just shows me kind of a stack. This is basically saying draw Toronto. Everything was somehow related to draw Toronto. There's my redraw function. And there's another redraw function that EasyGL is calling right away. Let's just double click on this draw function because that's the one I care about the most. So basically, when I double clicked on that, this draw function, I've now kind of zoomed in on it. And it shows me the draw function calls two things, draw all features and draw all segments. And draw all features is where most of the time goes. Draw all segments is where some goes. And inside draw all features, it's showing me that it calls feature order, it calls draw feature, get feature type, etc. And the number one thing is this draw feature. And inside that, I spend more time calling draw line than fill poly. So it kind of collapses the call graph that I just showed you into this kind of stacked bar chart. So I can click on any bar in here to see, well, how much time to spend in that bar and everything it calls. And then I can look, well, what were the things it called? Okay, so now I just went in a little further. I went, okay, let's zoom in on draw feature, right? Again, it's mostly line, some reasonable amount on polygons, and a reasonable amount figuring out whether something's closed or open. So maybe I could actually make this faster, and maybe I should just draw fewer lines, change my level of detail modeling. Okay, so let me go back to my slides quickly. Basically, I think that is it. I just showed you, the slides just kind of are pictures from that same call graph. So I basically went through all this already. And yeah, so that is, I basically did the demo, and those last slides are what was in the demo. So thanks, everybody. I think I'm basically out of time. So if you got any questions, come up and ask me. And if you're for the next tutorial, we'll get started in the next couple of minutes. Hey. I'm just going to stop the recording really quickly. Let me just quickly stop.